Hi, my name's Zach. For this part of the developer walkthrough, I'll be going through procedural generation in all its forms, as well as Perlin noise that comes with it, which is how it's all done. So I'm going to start off by showing you what happens when you press play on the scene, and just giving a quick walkthrough. So this is the terrain once it's been generated. As you may have noticed briefly at the very start, there was nothing in the scene at all. It was empty. This is all done as soon as you press play. So as soon as the scene starts, it generates the terrain, places the walls and the enemies, as well as some health packs dotted around the map, you might notice. This is all done through the use of Perlin noise, which is basically a pseudo-random computer-generated noise as such. It's grayscale, so it's either white, grey or black, and the way it does it is the computer assigns a colour that it gets using a function inside of Unity, with a random float for each element, which is the nature of the Perlin noise. It gives it a random float between 0 and 1. I then use that float I get to assign it to each the red, green and blue respectively values of a colour, and that's now the colour of the Perlin noise, and it adds it to a 256 by 256 grid. If I go onto the plane here, you'll see this is the width and the height of the Perlin noise, and these other variables I'll go into quite quickly. But it basically generates the terrain using this. So we'll go into the script now so you can get a better understanding. So again, these are the same variables that declared before. The width, the height, the scale, the height scale, both offsets for the normal offsets, the Perlin grid size, step size offsets, sorry, and the variables that hold, and the arrays, sorry, as well, that hold all of the prefabs that we're using. So starting off, we'll go into the start section. So this basically decides the offset of the Perlin noise. So once the computer generates it, it generates a 256 by 256. In order to help it not be completely the same, it generates a random range between 0 and 99,000, and that decides the offset of where the small grid is looking at the noise that the computer generates. So when you look at it, it will always be a different section of the Perlin noise. This greatly reduces the chance that you encounter the same level twice. Next, we set the height scale. So this is basically a random range between 5 and 15. I'll explain this a bit later, but effectively for now this determines the height of the terrain. And then you call generate texture and visualize prefabs. So move down to generate texture. Basically generate texture is what I used originally to set the Perlin noise to an empty UI element just to make sure that it was working. This is no longer needed now. This is purely for development size, just to make sure that the computer was actually generating what I wanted it to generate. But as of right now, this is still needed, but the display aspect here and the visualization UI isn't needed. So every time generate texture is called, it generates a new Perlin noise. So it goes through every X pixel between the width and the height and every Y, and sets the sample, which is the color, using calculate color when you give it the X and the Y. So for each pixel it sets a color, and then it uses noise texture to set a pixel, X, Y and the sample. So it sets that pixel to that color. So we'll move down to calculate color now. So calculate color takes both the int X and Y of the current pixel location, sets them as two floats where you get the float of the X, you divide it by the width, times by scale and add the offset. So this takes a position of it and just shifts it. It then takes that float and uses math.perlin noise with the X coordinate and the Y coordinate, and it sets that coordinate as the color using the sample float that it just got using the Perlin noise function. This gives us the different colors, the white, the grey, the black. Going back up here, you now notice that we call visualization prefabs, so we'll move down to visualization prefabs right now. This creates a new empty game object called parent, which is just a nice way to organize everything, keep it all in one object so it doesn't completely flood the scene. We set the transform as this.transform, so whatever this is attached to, this new game object becomes a child of this. And then we start looping through the pixels of now the Perlin grid step size. So the Perlin grid step size is the, back up here, we name it at the start and we go back into the Unity scene. We've set it as 80. So this is a way to scale it inside of the Unity scene. So we assign every pixel inside this Unity scene of an 80 by 80 grid, and that is now the size of which this generated terrain becomes. So go back into the scene now and we scroll back down to visualization prefabs. So now we're cycling through every pixel or every X and Y in the grid step size, which is now an 80 by 80 grid. We're now doing color checkers calculate color, so we're making sure that the color is, we're setting the color that we're checking against is in fact, so we fetch a color using calculate color again, and we'll go down here and now we'll be checking against that color, which is what this commented out code here did. We've now moved it around a bit here. So we get a bunch of random ranges here for random select, so this is the prefab with the length, and random enemies for enemies.length. Now this range here isn't technically needed because as I mentioned before, the original goal for the procedural generation was to have a bunch of cover objects and buildings and stuff and it to randomly pick one from an array. We ended up scrapping that and going with generating the terrain, so that array is technically only one element long and it's just one cube. So this is picking a random number between 0 and 1, so it's always going to pick, it's picking one element each time. So you could just hard code it, but I kept this in because, like I mentioned, this was from the previous one and it worked for the current one, and it meant if we wanted to ever expand upon it, we could always do that. This is the same for enemies, but obviously there's more than one enemy, so this is why that code came in handy. We use the same code again to check the enemy length, but for the 3 different enemies. We then get a float with sample stepped, and we'll quickly jump into sample stepped. This takes the grid step size that we have defined here, which is the width of the Perlin noise divided by the Perlin grid step size. So this is now the grid step size. So you divide the width of the Perlin noise by the actual physical space it takes up to get a new grid step size. And then to calculate the float, we do the noise texture.getPixel, and we're doing a floor to int, so we get rid of the floats now. And we're doing x, which is the current x and y we're passing in, times the grid step size for both, and setting it to dot grayscale, and then we're returning the float. So this float now, we go back into the other code. This is now a float of what the color was. We'll keep that for later and we'll use that. So for game object, we're now instantiating the prefab that we want, the a new vector, which is x in the grid, sample, which is the color float that we got from earlier, times by the height scale. So this determines the height of the block, or cube in this case, that is being placed at on the y. And for the z, because we're looking at a 2D to a 3D, the y is technically the z, so we set the z to y. We're then adding the transform.position and rotation of the current object it's in to make sure they're all facing the same way. We're then spawning in the set parent, and that's when we actually spawn it in and set the parent, and that's that. So this here is used for purely for creating the cubes. So this instantiates every single slot in the grid as a cube. These other 3 ranges here are for the enemies and for the walls. So by doing this, as well as health packs as well, I should add, sorry. So we have 3 different ranges here which determine the occurrence that they happen. So we want a lot more cover, so it's between 0 and 40, so there's a high chance it gets 1. For health, it's to 1 and 2,000. We don't want too many health packs. And for 1 and 1,000 for enemies. We want more enemies and health packs to provide a level of difficulty to this. So this is the same code 3 times. We're doing it if whatever int that we're using for the range respectively is 1. We're then creating using the same code up here to instantiate the prefab that we wanted, timesing it by the same position, so it's x for the current position, sample times height to get the same height. But as for the walls here, we want a random range, so we're adding on to that height a range between 1 and 3. This allows the cover to be at varying heights, so you can have taller cover or shorter cover. This is purely for the walls. And then we're mining a slight offset because there was an issue when we were spawning it in, and we want to offset it slightly so it fits a little bit better. And then we're doing transform position rotation as well. Same as before, we're spawning and setting the parent object parent. So this now becomes a child of the object we created at the start of the code. Again, these two do exactly the same for their respective aspects. The only one difference here is for the health packs. We added in an extra check so that the health packs don't spawn in the same place where walls did. So you don't have any collisions like that. And that's visualized prefabs. We've already gone over sample stepped. So this is effectively creating Perlin noise, generating it, the computer's then reading it in pixel by pixel and generating terrain based on it. So I'll go through a couple. Start and play a couple times so you get the sense of the terrain. So you notice here that this terrain right now is kind of it's much hillier and there's much more variation in the height. If I then stop it and start again, hopefully we'll get a much shallower terrain. So here, you notice the valleys aren't as deep and it's much more compact. So this is because of the random range of the height we set between 5 and 15. So this picks a random variable between those two, a random number, sorry, and it sets that as the height multiplier. So every time it times a cube, it times it by that, so the heights are always different, and you get nice looking terrain. And yeah, that's Perlin noise and procedural generation. Thanks for listening. Here's an example of Perlin noise. This is what the computer generates and is stored within the script.
Hi, my name is Nick and I'm going to be taking you through my script of the code review. The first we have is the follow mouse. It is a very simple one. All it does is get the mouse position from the input of your actual mouse and then converts it to the world position and then sets the transform or the objects on to the point. This is used for when we have a particle effect as the mouse for like the main menu or the end screen, where it has the green neon line effect that follows the mouse around, so you can see where you are clicking without having to use the actual cursor image itself. The next script is for the health bar system. It's very simple. All it does is get the slider object and a back bar, which is the color underneath it, so when you get hit it lights up. So all we do is we set the max health. We have a method for that. It just sets the max value of it and sets the current value at it. So at the start it sets it as, it also works in the health system, so at the start health system it sets it to 100 and it resets, so it sets the value and the health both to 100. And then we've got a set health for halfway through, so when the player gets taken damage, it sets the value to the current health. So the health will then be, say it's 100 and you get damaged by 10, it will send the new health, which will be 90 or so, to it, and then set the value. And it also does a little animation for hit. It sets a trigger, and all that does is just flash it red quickly, just as a bit of feedback to the user that he has taken damage, and it's a bit more noticeable that it is changing. The next script is for load and score. This is used on the end screen. It's quite a simple one. All we do is you get two text objects and we set two strings which the score and the level is going to be around, and initialize a couple of integers. After here we get the player prefs for score and levels. These are set when the game ends and you move to the end screen. They are set so after you complete a level it increases, or when you kill an enemy the score increases. And then we just set the text object to the new strings with combining these together. Menu navigation is a bit more trickier. To begin with, we have 3 game objects with player, weapon and crosshair. These are going to be disabled when the player press pause, so this will stop mouse movement, firing and the crosshair, because you don't really want a crosshair on it. We then have UI controllers. These are for the main screen there. This disables, when you click on the controls button, it will disable the start button and that, so it will hide them and show the actual controls, so it enables these two and disables these two at will. And then we have a ball and pause menu, so this is just simple to check, see if it is paused, and if it is paused it will do the opposite basically as this method does it. So it makes sure you're in the correct scene, make sure I'm not pressing escape on the front screen because it's also used on the main menu and end screen. It then checks if you're pressing escape, which is the pause button, and if it is paused it will play resume, or vice versa, it does the opposite. Then we have a lot of methods. This is just scene manager, load scenes. These are loading the scenes throughout, and we also have some set ints and that for when you do this. These are very simple, it's just Unity scene management, very simple. And so resume and pause are basically the opposite of each other, so I will only explain one. It locks the cursor in a mode, it unsets its pause, it sets, so this is when you press resume, so this goes back into the game. You then enable all of the stuff I've disabled, so this will be the mouse movement, firing and that. Enable the crosshair and deactivate the pause menu, so that is now hidden, and as I said that's just backwards. We got just display controls and that, so this is when on the main menu when you press controls, it activates the controls and the button, just shows them and hides the stuff underneath, so the logo and the panels it will. It's very simple. On the pause button, I had to create an event for when you click it. This is very simple just to play it again, because as you pause it, you set time to 0. So it doesn't work the same as animations or buttons. It doesn't always, and we had a little issue where sometimes it was, sometimes it wasn't. So to make it thing, I just create my own event. And for the final script, it is to select the weapon. It's quite a simple one. It uses a game object and a text. It gets the game object of the parent child, of which holds all 3 weapons classes in. It then runs through, so this is happening every frame. It runs through the weapon class to get so there'll be 3. If you want to add more weapons, it would work with that. It runs through it, and if the object is enabled, so how the weapon system works, it disables. So if you use the cannon will be enabled, and the other 2 will be closed, and it swaps out of that. It then, if it is true, so that is the gun you'll be currently using, it sets the text to the text and the name of the child, which is the weapon you're using, so cannon, rifle, or laser. And that's that. Thank you for watching my code review.
For my part of the developer walkthrough, I have chosen to split my content into 2 sections. The first being all the movement in the game, and the second being the weapon and health systems. We start with possibly the most basic script, called Look. This script is designed to be placed on an enemy, and to be given a target to look at. In the start function, if the script has been given nothing to look at, it will simply destroy the game object as to avoid an exception. And in the update function, we're simply taking the target's position and looking towards it with an inbuilt function called LookAt. The method addScore is in this script as it was a convenient place to access the number of enemies killed. It simply accesses the player preferences file and looks for total enemies killed and run kills, adds 1 to them, and then restores those values. Our next script is pointAtPlayer. It performs much the same function as LookAt, however it's not limited in the y-axis, like Look is. This is because we wanted the entire enemy prefab to be looking at the player, but only certain bits of it actually pointing at the player. This script is also where the enemy decides to fire its gun. In every frame, delta time is subtracted from the remaining time, and if there is no time remaining, the gun fires. Fire gun then sets start fire in the weapon component of the enemy to true. This will begin the firing process. The script enmove simply moves an enemy towards a given target. In our game, we have added separate game objects that pick a random position, which I'll get into in a minute, and then the enemy moves towards them. As mentioned, we have a separate game object that controls where the enemy will be headed towards. As each enemy is designed to move at different speeds, and in different manners, the time remaining in this case is public. This allows us to set each enemy a different number of times per minute that they will change direction. In the update, again, the time remaining is subtracted from by delta time, and if there's no time remaining, the script picks a new position and moves the cube it's attached to that position. The score system script is how we keep track of a player's score, and also how we know to reset the scene when all the enemies have been vanquished. The update function simply searches the hierarchy for any objects with the tag of enemy, and if there are none, then it takes the stored variable of reset number, or reset no for short, adds 1 to it, and then restores that value. The scene is then reset using the scene manager. Smooth move is definitely the most intense script to look at, however it's not particularly complicated. To ensure that the user has a smooth experience on our slightly bumpy terrain, all sorts of checks are necessary to make sure that the user is able to jump when they want to and move in the directions they want to without impedance. The basics of the script are that it takes the mouse's velocity and position and the current input from the keys to ascertain the direction the user wants to move in. It then checks to see if this movement will collide with the terrain and if the user is already jumping. If they won't collide with the terrain and they're not jumping, then the user is allowed to move in this direction. If the user is in the air, they still have limited control over their mobility, but will not be able to turn and change directions quite as quickly. This is all performed using gravity and different velocities. Our next section is the health and weapon system. Our first script is Bullet. This is the script attached to any of the bullet prefabs in our game. It sets the bullet's movement speed, the damage that it does, and the time that the bullet will fly for before evaporating. In every frame, it checks to see if it has any time remaining, and if not, then the bullet dies. Before the bullet dies, if it collides with anything, it tells the thing it's collided with to run the method take damage. This only applies if the thing it's collided with has a take damage method. We then run the function spawn die, which is much like the die function, except it spawns particle effects to show that the bullet has impacted. Once the particle effects have finished, the bullet is destroyed. Health pack is almost exactly the same script, however the health packs have no need to move in the scene, and so that functionality is removed. And instead of the take damage function, we run the function get HP. Health packs also last forever and do not have a time to live. Our weapon script takes a bullet prefab and a transform called bullet spawn, and whenever it receives the call to fire the weapon, will spawn the bullet prefab at the empty transform of bullet spawn. To stop players and enemies being able to fire at an infinite speed, there are a couple of checks to make sure that the user is not already firing, and that they can actually fire. If the weapon has any audio attached to it, it will play this audio upon firing the weapon. The weapon script is written in such a way that it can be applied to both enemy and player prefabs without having to add any additional code or extra scripts. The weapon manager script is for the player and the number of children in the hierarchy the player has. Because of where this script is placed, the only children the player should have will be weapons, and this script enables the user to switch between them with the scroll wheel or the number keys. It does this by counting the number of children in the hierarchy, and then enabling and disabling the other children in the hierarchy as you change weapons. Similarly to the weapon script, the health system script is supposed to be applied to both the enemies and the bullets and the player. This means that with one script, bullets can be shot out of the sky, enemies can be shot out of the sky, and the player can be killed. In the start function, we make a simple check to increase the enemy's health, to increase the difficulty as the game continues. We also check to see if a UI element is present, called health bar, and if it is, then we set its minimum and maximum values. Health system is also where take damage, referenced before, and get HP, also referenced before, are kept. Take damage takes the current health that you have and subtracts the damage that was passed to it from the health bar. If the health is less than 1, then it invokes on die, which is an event we set up. This is because there are different things that happens when the player dies versus when an enemy dies and when a bullet dies. If the player dies, then game over is called, the total score is calculated, and the end scene is run. If an enemy dies, it destroys the enemy. And in the editor, the event is used to call add score from the previous script. And finally, cover cubes. Cover cubes is a simple script to check if the pink floating walls in the sky, added for aesthetic reasons and something to put in the skybox, are colliding. If they collide, then they destroy each other. It does this by checking for the tag cover in the thing it's collided with. This enables it to collide with the exterior walls and bounce off of them.